Hi, this is Dr. Simon Romero and I'm here to present you the video tutorial for section 12.4, the cross product. In this section, the thing that we're going to do is we're going to talk about the idea of the cross product, the definition of the cross product, areas and cross product, properties of the cross product, and parallel biped and triple scalar product. These are the practice problems. As always, I suggest you to do them all. The idea of the cross product. We want to define a new product of vectors. Now we want the result to be a vector, unlike the dot product. This vector has to have certain properties. It will be orthogonal to both vectors. Remember, orthogonal means that the angle between them is a right angle. The direction is given by the right-hand rule, so it has to be orthogonal to V and W, and it's going to be pointing at following the right-hand rule that we have seen before, and the magnitude is going to be equal to the area of the parallelogram determined by both vectors. So in this case, it's going to point at the direction of the thumb of the right hand, and it's going to be the length is going to be the area of the parallelogram. So geometrically, this is what will we have. So always remember the result of a cross product of two vectors is a vector. So the vector cross a vector is a vector. The definition of the cross product is going to be this. You see, I mean, I given the two components of the two vectors. The cross product is going to be this vector that we have like that, or in IJIK, this is the one. This is the way that you will obtain the cross product. So I know what you are thinking. And the answer is yes. I'm expecting you to remember this, but I'm going to give you a little trick to remember it a little bit better. For that, I need an operation called determinants. The 2x2 determinant is an operation defined in a square arrangement of numbers that has two rows and obviously two columns. And the way that you compute the 2x2 determinant is you multiply the members of one diagonal, the diagonal that I'm showing here, this diagonal, and then you subtract the multiplication of the vectors that are in the other diagonal. Notice that the order is important. A 3x3 determinant is actually the one that is going to be useful for us. But in order to understand the 3x3 determinant, you need to understand the 2x2 determinant. So how do we compute the 3x3 determinant? By definition, it's going to be as follows. You're going to take the number in the first row, first column, and then you're going to place it there. And then you're going to erase all the numbers that are in the same row or column as you want. The numbers that are left behind, you're going to take the determinant of those and multiply it by U1. Then you're going to put a minus. This minus is very important. Usually students tend to forget about putting this minus. Then you're going to place U2, and then you're going to do the same thing. Erase row and column and put the determinant of the remaining numbers. Then you're going to have a plus, and then you're going to put U3, and then the determinant of the remaining numbers after erasing row and column where U3 is. So that gives you this computation over here. So you may wonder, well, why this is useful. Before doing that, let me just work an example. Remember, every time that I'm working an example, you can I suggest you to pause it, pause the video, try to do it on your own, and then check if your answer is correct. So let me start. I'm going to put 1, and I'm going to erase row and column where 1 is, and I'm going to take the determinant of the numbers that are left behind, and then I'm going to take 2 with a minus, extremely important minus, erase row and column where 2 is, and then the numbers that are left, I'm going to take a 2x2 determinant, and then I'm going to do the same with 3 and put it down, and I erase row and column where 3 is, and then that's the determinant of the numbers that are remaining are going to be the determinant is going to be multiplying 3. I do that, I do the computations, and gives me that that's equal to 0. I mean, you will see later on, if you understand very well what we see at the end of the class, you will see that the determinants are important in order to check whether vectors lie in the same plane or not. 3 vectors lie in the same plane or not, and that's going to be useful also for linear algebra. Let me talk about a little bit about the cross product using determinants. So you have the cross product, you have the 3 by 3 determinant, and notice that these two expressions are almost the same. The only difference is instead of having I, j, and k, you have u1, u2, and u3. So here is the way that we're going to use determinants in order to remember cross products. The thing that we're going to do is, if you want to take the cross product of two vectors, you just write in the first row I, j, and k, the second row the first vector that you're taking the cross product, and then in the second row the components of the second vector that you're taking the cross product. In theory, this expression is not technically correct. It doesn't make sense because I, j, and k are vectors, and if you remember, I told you that the determinant is an operation defined on a square arrangement of numbers, but we use it because it's very helpful. It gives us an easier way to remember how to compute the cross product. Let me give you an example. Again, if you want to pause it, you should do it right now and try to do it on your own. Since A cross B gives us a vector orthogonal to A and B, the only thing that we need is to compute it. So let's set up our determinant, ijk, then we write the components of A, we write the components of B, and then we take A cross B, and it gives you this vector over here. So this is our answer. Now, there is an easy way that you can verify if your cross products are correct. That means that you take your result and take the dot product with the original vectors. Take the dot product with A and the dot product with B. If those two dot products give you equal to 0, that means that your computation probably is correct. If for some reason it doesn't give you equal to 0, it's a good way to detect that you made a sign mistake somewhere, and then you have to recheck your work. Notice that in the first one it gives us equal to 0, and taking the dot product with the second one, in other words with B, our result also gives you equal to 0. So that means that we didn't make any kind of sign mistake. The geometric representation of the dot product is related to areas of parallelograms and vectors. So every two non-zero vectors determine a parallelogram, just the way that I'm showing here in the picture. And the formula for the area of a parallelogram is the same as the formula for a rectangle. The area of a rectangle is area of the base times height. Notice that in this case, the base is just going to be the magnitude of B. And the height is going to be, well, it's given by trigonometry, right? If you have the angle between them, then the height is just going to be the magnitude of W, that happens to be the hypotenuse of this triangle, times the sine of the angle between B and W. So remember that we said that the one of the properties of the cross product is the magnitude of the cross product is going to be the area of the parallelogram. Well, it happens then, in other words, we have that because that's the area of the parallelogram. If you want to know why the magnitude of the cross product happens to be the area of the parallelogram, because remember, we define the cross product in a different way with components and determinants, you will see that in our next activity. Areas and the cross product. So let me give you an example of how you can find areas by using the cross product. Find the area of the triangle with vertices, those points in the space. So the idea is going to be the following. Again, pause it if you want to do it on your own, and then I'm going to work it out. So take the point P, Q, and R, and I'm going to put them there. This may not be precise, but this is just like a little drawing sketching you the idea. And the thing that I'm going to do is I'm going to draw the vector PQ and the vector PR. So in other words, we need vectors in order to do operations with vectors. So if you take the magnitude of PQ cross PR, that gives you the area of the parallelogram. Now, the triangle that we're looking for is just half of that area, so the area of the triangle is half of the magnitude of the cross product of PR and PQ. So in this case, PQ is equal to that, PR is equal to that, and the thing that we have is, again, this is our determinant. Later on, when you are used to taking cross products, you may not need to write the determinant anymore. But in this case, well, I'm just putting it in there so you can identify it. And I take the cross product of PQ cross PR, and that gives us this vector that we end up right here. Now the thing that we do is we take the magnitude of this vector, and the magnitude of this vector happens to be 19, and if we divide it by 2, I'm sorry, I went too far. If we divide by 2, gives you the area of the triangle. So it's 19 halves. So let me give you the properties of the cross product. The properties of the cross product is the cross product does matter which order you take it, and that's just because of the right hand rule. If you change the order, the only thing that is going to happen is you are going to have a vector that is going to be flipped. In other words, it's going to point to the opposite direction if you change the order. These next three properties are just telling you algebraic properties. You can take constants out. That is going to be very helpful when you're trying to simplify cross products. And the other two are just ways that you can FOIL or take common factors. Finally, this one I'm not going to talk too much about it, but it's just for you to know. Then if two vectors are parallel, then the cross product has to be equal to 0, and if they are orthogonal, the magnitude of the cross product is just going to be the multiplication of the magnitudes. Let me tell you a little bit about the scalar triple product. The scalar triple product is going to be the combination of the dot product and the cross product, just like we defined here. Notice that the cross product is equal to that, and the vector u is equal to that. So when you take the dot product, you just multiply components. So in other words, we're doing this. Well, at the end, notice that this is just a 3 by 3 determinant. So it has an easy way to remember the scalar triple product. Actually, an easy way to compute it is just computing the 3 by 3 determinant of the corresponding components. Well, why this is useful is because it's going to help us to compute volumes of certain kind of geometric entities that are called parallelepipeds. A parallelepiped is just a three-dimensional version of a parallelogram. So the way that we compute the volume for these things is just area of the base times the height. In this case, the area of the base is very easy to compute because it's just the magnitude of the cross product between B and W. And the thing that we have is, what is the height? Well, the height, notice that, let me just compute the cross product, B cross W, and then I will let you know what it is. Notice that here we have B cross W, and the only thing that we're doing is we're taking the component of U into B cross W. The volumes of parallelepipeds and the triple scalar product then is area of the base times the height. You have that. Then I use the formula for the component, and you end up that the absolute value of the triple scalar product is actually the volume of the parallelepiped. Well, thank you very much for listening to this video, and I hope that you understand a little bit better the subject.